Okay, so in this part of the lecture, I want to give you one last example of ring opening, ring closing, but starting with the ring and then move on to a total synthesis example. So this will be example number 3. And again, everything is in the starting material. So we don't need an extra alkene. It's all intramolecular. And so let me go ahead and start right off with the catalyst. If you're noticing, we are forming 2 7-membered rings, and of course, the 5-membered ring in the middle. You can already see the making of the 5-membered ring or the 5-membered ring that's already there, right? The 5-membered ring has no double bonds to it, so it's not going to break open. The Grubbs metathesis is specific to rings and acyclic structures with double bonds. So all the chemistry is happening with anything that has the double bond in it, okay? i.e. the ends of it. So let's go ahead and jump in. Oh, excuse me. So that is my carbene is where I usually draw it. And what I'll do is I'll try to draw it 2-dimensionally. This is 3D, and so it makes it a little hard to see sometimes. If you can see it, by all means, that's more than fine. But I'm going to draw it 2-dimensionally. This is a bridge, right? So the way that you would draw this system is as follows. Okay. And of course, please notice I need to draw out my bridge, so I need to draw it wedged, coming out towards you. So there's my bridged system. I'm just drawing it again 2-dimensionally just so that it's easier for me to see. If you want to keep it 3-dimensionally, that's perfectly fine. If you can see it, awesome. But I'll just draw it 2-dimensionally. So the first thing that we have is ligand association, and we introduce our alkene. And as I mentioned before, I am going to do this starting off with my ring. Ligand association. So there's my first ligand association, followed by ligand dissociation. You notice The ring is a symmetrical ring, so you can really start with whichever you want, whichever side you want. We do our migratory insertion, our pseudo-migratory insertion. And we form our four-membered ring. I.e. our metallocycle. Notice that we haven't broken our bridge. All the chemistry is happening with that double bond. Everything else stays intact. And then, of course, we do our collapse. Let me call this our metallocycle to stay consistent with our other mechanisms. Now, typically our collapse includes the formation of styrene, right? In this case, because we're starting with the ring, we don't have styrene. Our byproduct, i.e. our double bond between the two carbons with the phenyl group, are part of our product. So this is usually what we see, is the styrene part of the molecule fall off on its own. Now it's going to stick around as part of our product. And not only that, of course, but the ruthenium also becomes part of our structure. But notice that when you open up the ring, it opens up the ring, but it also allows you to see the five-membered ring that's there. Okay? So let's draw out the five-membered ring first, which is what I've highlighted in yellow. You can see the five-membered ring. I'll start with hopefully the easy stuff, i.e. the substituents at the bottom. So you can see that. And then I'll move on to what feels like the harder part. I'll do the right side first. Let me highlight that in blue. And notice that the carbon on the five-membered ring is bonded to that carbon, double bonded, and then to the phenyl group. And then the carbon on the other side is the ruthenium carbon. And so I'll add my substituents to this as well. And I've introduced my ruthenium to my skeletal structure or my ring structure. But by opening and breaking that bond, I've exposed the five-membered ring that's already present. So if you look at your product, there's my five-membered ring. So you can see what's going to start happening now. Now that I've opened up my ring, I have to start doing ring closing metathesis with the next available double bonds. Okay. So now we've got ligand dissociation, right? And so we have to make sure that that double bond is pretty close to the ruthenium. Let me draw out my five-membered ring. I'm not worried about my right side right now. I'll worry about that later. And I have to worry about it just because it's got my benzene ring on there. I need that benzene or that phenyl group, excuse me, back on my ruthenium. So I'm going to have to come back to it. But what I care about right now, not surprisingly, is the formation of my seven-membered ring on my left side, since my ruthenium currently is on the left side. Okay. Okay. So there's my ligand association. Is this going to be a seven-membered ring? You should number your carbons to see if you've accounted for every carbon. So 7. And so you can start seeing that it's going to form a seven-membered ring. Just like before, we do our pseudo-migratory insertion. To form our metallocycle. So not only are you forming a seven-membered ring, but you're forming a seven-membered ring with a fused four-membered ring. Let me draw my seven-membered ring. And number it as I'm coming along. After a while, I know it's really hard to draw out these seven-member rings or eight-membered rings. I'll call this carbon 8. They get a little bit easier with time. And so I formed my seven-membered ring with my ruthenium metallocycle. And so you can start seeing how it's looking like your product, right? It collapses. And now I formed the double bond in my seven-membered ring, which is present in my product. And there's the left side of my molecule. Now I need to move on to the right side of my molecule. This is the byproduct that I made. And so I go in and now I take care of the right side. Okay. And so let me go ahead and move on with the right side of my structure. I do ligand association. You can start with whichever double bond you want. In order to form that seven-membered ring, I just have to introduce the ruthenium to the innermost part of the structure so that it becomes part of the skeletal structure, right? In order to form that ring, that ruthenium has to be part of this huge skeletal structure. So with whichever alkene you decide to start with, the ruthenium has to be part of your uh, innermost part of the chain. So, oh, let me show you. I'll start off with the top alkene, but completely up to you. There's my ligand association. Let me do my pseudo migratory insertion. Let me start going back. And you formed your metallocycle. It collapses. And FYI, if you start with the top, you form styrene. So there's your styrene, and my ruthenium is not part of my structure. Now I know I changed this dash to a line. I apologize for that. It should continue to be dash. It's hard to keep track of everything. So it should stay dash as well. Okay. So there's my left side. Now let me do my right side. Oh, excuse me. Not surprisingly, again, now I do my ligand dissociation. Please notice how I've maneuvered my allylic system so I can put it really close to my ruthenium, right? Let me redraw this. So there's my ligand dissociation. I do my migratory insertion. Again, let's count our atoms to make sure that we're forming a 7-membered ring. And it looks like we are. Carbon 1 and carbon 7 are the ones that are going to form the bond together. And so I have formed my second 7-membered ring. Just really clever chemistry. And just like before, you're not only going to have a 7-membered ring, but you're also going to have a 4-membered ring fused to it, right? So it looks exactly like what it looked on the left side. It's the exact same mechanism. You have formed your metallocycle. Sorry, I forgot to write out pseudomigratory insertion. It collapses, and I have formed my 2 7-membered rings. Just really clever. Plus my ruthenium carbene with carbon 8. Okay. And of course, our desired product from above. Okay. And then, of course, we introduce the styrene. I know we keep doing this over and over, but we kind of need to keep track of have we finished the mechanism, right? If we haven't formed our catalyst, then the mechanism isn't done. We have to keep going. Dissociation. So just bear with me. Form ethylene, our precursor, and finally ligand dissociation to form our catalyst. Ooh, I'm a little far. Okay. Just really clever how everything was done. You can start from an end, you can start from the ring, whichever side works best for you. Okay, let me finish this part of the lecture by introducing a total synthesis. This is one of my favorite syntheses. So this is the total synthesis of clavilactone 8. The enantiomerically pure, it has anti-tumor activity. And of course, just like in previous syntheses, I'm not going to introduce the entire synthesis. I'm just going to introduce um, the parts that are relevant to the organometallics that we've been discussing. It is a pretty overwhelming structure, so give me a second to draw it out. And in this case, I will take a couple of shortcuts when writing out the structure, just because we're not talking about the entire synthesis. Oh. So you can see why it's an overwhelming structure. Let me number this. It is a 10-membered ring, first of all. Not only that, it is a lactone. And you guys know, hopefully, that a lactone is a cyclic ester, right? So hence clavilactone. It's a cyclic ester. And within that ester, there's also an epoxide to it. Okay. And so the synthesis, or the main parts of the synthesis, come in 3 steps. Again, we're not going to go over the whole thing. It's just 3 of the major steps that are thought were incredibly important. So I want to draw this in black pen. Mm. The first step, or the first major step, which I'll call step A, is the formation of the lactone, i.e. the cyclic ester. And this is all chemistry you've seen before. Which is what's so great, because we really just learn reactions, but we don't understand their relevance until we apply it to a total synthesis. So that's the first step, is the formation of the lactone. Step B is the introduction of an alkene group. Oh, and not only the introduction of the alkene group. Ooh, I got my black pen. But the formation of my epoxide, which you learned in second semester organic chemistry. And then finally, step C, your natural product, Clavilactone. I'm going to go through these steps briefly. What I would like to start with, obviously, is step A. And so I know that I drew it above as follow. Ooh, as follows. But what I'll do is, to save us time, I'll just call this my aryl group. AR for aryl, since that's not part of my first step mechanism. Okay. I don't want to keep drawing that aromatic group with the phenyl, excuse me, that aromatic group with my bromines and my methoxy groups. I just want to leave it as is. And so step A, not surprisingly, is a ring opening, ring closing metathesis. You introduce your ruthenium catalyst. Just really clever how they came up with this strategy. You can start with whichever double bond you want. Again, the ruthenium has to be part of your skeletal chain. Again, I don't typically start with the ring because it can be confusing to me, but if that's the easiest for you, by all means, do that. I like to start off with the chain. And so I'll go ahead and complex that first. I've got my ligand dissociation. I've got my ligand dissociation. I've got my migratory or my pseudo-migratory insertion. Again, the ruthenium adds to the more substituted carbon. It wants to be part of the chain. I can't stress that enough. I've got my metallocycle. Ooh, it now collapses so that the ruthenium is part of the chain, and I form, as always, styrene. And now I've got my ligand association. So I'm just going to redraw my structure. There's my ligand association, followed by my pseudomigratory insertion. Let me see if I have room to go back up here. Let me give myself a couple of more room, a little bit more room. If you need to number your carbons, number your carbons. Am I going to form a 5-membered ring lactone? And it looks like I am. Carbon 1 and carbon 5 are going to bond to each other. So it's collapsed. I have formed my 5-membered ring. Again, let me number it so I can see where everything is bonded. My carbon 1 is still bonded to my ruthenium. My ruthenium is now bonded to carbon 6. And I still have a 4-membered ring. So just like before, it's 3 fused ring systems. Just like before, it collapses. Here's my metallocycle. And collapses. Now let me draw this in red. And I have a double bond at carbon 1 and 5, which is actually perfect because I need that double bond, right? That double bond is crucial for the formation of my epoxide. Let me number this. There's my double bond between carbons 1 and 5. But 5 is still bonded to a chain. And give myself enough space. And now I can go ahead and regenerate my catalyst. So I introduce my styrene for my ligand association. It does the migratory insertion. Ooh. Or pseudo-migratory insertion. It collapses, and I formed not only the precursor to my catalyst, which I just need to add PCY3. Ooh, but I've also formed my first product. And we're done. Step A. So step A was our ring opening, ring closing, metathesis, or ring closing, ring opening, metathesis, which we just learned. Now let's jump into step B. And just to remind you what step B is, and I give myself enough room here. Okay. So the first thing is oh, excuse me. The first thing that they have is the epoxidation of your alkene. Ooh. With MCPBA. Followed by a Stille reaction. So they were able to not only epoxidize, so this is after MCPBA, and it was wedged in order to avoid any steric hindrance from the bottom. The other thing about this that I want you to note before we go on to the Stille reaction is that there's only epoxidation of this particular alkene. There's really no epoxidation of the terminal alkene. And the reason for that is because this is a much more reactive alkene. It has resonance, it's electrophilic, okay? And epoxidation requires a peroxy acid that's nucleophilic. So it's a much more reactive alkene than your terminal alkene. Again, if you remember epoxidations, this is just a quick review. Oxidations in the presence of a peroxy acid, okay, attack your alkene, attacks your oxygen to generate your epoxide and to form a carboxylic acid, okay? Because we have a conjugated system, right? This has resonance towards the carbonyl, making it an electrophilic carbon so that the oxygen can come in and attack. Really clever what they did, epoxidizing that alkene specifically. And then, of course, the next step is our Stille reaction, in where they introduced, it's one of the cross metathesis, in where they introduced their alkyl chain in place of the bromine, which we've talked about before, okay? So we're seeing two different types of organometallic reactions in this total synthesis. And then finally, step B, or step C, excuse me. Step C, to remind you again what step C looks like, because I know I didn't really write it all out. Once you've epoxidized, once you have your second chain introduced, you have to close up the ring, right? Because the clavilactone is a 10-membered ring. And you do that through Grubbs metathesis. I won't put you through that, but let me just introduce it. And that, let me show you their final product. For this reaction, obviously the final product is the clavilactone, but just for this reaction, and if you number your carbons, again, you form a 10 carbon ring, okay? The really last step is the removal of the methyl groups to introduce the hydroxyl groups that it's protecting, and that's pretty much it. Super clever on the total synthesis with respect to using Grubbs metathesis, ring closing, ring opening, ring closing, and the Stille cross coupling, excuse me. Okay. Okay, the next part of the lecture is just going to be cross metathesis. So intermolecular reactions, two different alkenes doing Grubbs metathesis. So you're not forming rings, you're just forming longer chains pretty much. Okay.